Welcome to Difference Equations, Lesson 4. In previous lessons, we studied first-order linear equations, and we even looked at some more complex cases that were non-homogeneous and non-autonomous. In this lesson, we're going to look at higher order, in particular second-order linear equations. We'll have a method known as characteristic roots that will allow us to solve these second-order equations. The method applies to higher order, but in the examples, we'll be looking at second orders. And then we'll look at and solve the Fibonacci sequences and the associated Binet formula, and also a similar sequence to the Fibonacci known as the Lucas sequence. So just a summary of where we're at this point. In lessons 2 and 3, we solved a general equation for first-order linear equations, if you recall, and I reposted that on several slides, and then we specialized it for different cases. What we want to look at now are higher order. As I mentioned in the intro to this lesson, we'll focus on second order. So you notice this equation here on the right. In order to compute xn plus 2, you need to look at the prior two terms. That also implies that we'll need two initial conditions in order to solve this. And the techniques that we used before, where we again used that general solution for the first order and then specialized it, it really doesn't work here. It becomes intractable. But fortunately, there's another technique that works out fairly well, and I'll get to that on the next slide. Here's the method of solution that will guide us to finding the closed formula for the higher order equations. We assume the solution is the form lambda to the n, and we substitute that into our, in this case, second order equation, the one we had on the previous slide. We have this here. Then we divide by lambda to the n into this equation, and we get this second order equation. So you can see where this would work for higher order. You would make the same type of guess, and then you would just get a third degree or fourth degree or so on equation to solve, which is, as we know, are more difficult. And so we'll focus here just on second order, but it works in higher degrees. So yeah, as I mentioned, this difference equation becomes quadratic. Lambda to the n is never 0. So dividing by it is legitimate. That's just here referring to this where we divided by lambda to the n. An equation of order k gives a polynomial of degree k. So the method scales. That's what I just mentioned previously. For a quadratic equation, there's three cases. We have distinct real roots. Let me point to it. So we have two distinct roots, and that'll be the case when we look at the Fibonacci and Lucas sequences. Then you can have a repeated root where you have the same root twice, or so in other words, when you factor something like this, you get x minus 3 squared, and so 3 is a repeated root to the characteristic equation associated with this one. And then you can get a complex roots, and there's a solution in terms of powers of sine and cosine. So we have an example of that at the end. And in general, for higher order equations, you can get combinations of these things. You can get pairs of complex roots, you can get repeated roots, and then you can also get just single roots. But again, we're just going to focus on quadratic equations or second order equations in this lesson. For our first example, we'll take this linear difference equation. It's order 2. If we let x sub n equal lambda to the n, That means x sub n plus 1 is lambda to the n plus 1. And then this term here is lambda to the n plus 2. We factor out a lambda to the n and divide that on both sides, and we get this equation here. Then we use the quadratic formula to find two roots. The general solution to this, which we'll demonstrate on the next slide, is x sub n equals c to lambda 1 to the n power plus d times lambda 2 to the n power. And we can prove that this works. We'll do that on the next slide. Before we find a specific solution, we can do a check just to show that our general solution here is a solution to the difference equation down here. So we already showed this on the last slide. Then we can just write down x sub n plus 1. This will be to the n plus 1 power, but I want to just isolate x to the 1 to the n and x sub 2 to the n. So I just factored that out. And then x sub n plus 2 can be written this way, again, making use of this equation. Then you plug this, and this into here, and you collect terms, you group terms together. So you have the terms involving a c here, and all the terms involving a d here. And you notice that the lambda sub 1 to the n is in the first term in all three of these, so that gets factored out. The same thing for lambda sub 2 to the n, that's in the second term in all three of these. And so you get this here, and then this is the our initial characteristic equation, and we solve this. We know that this is 0 when you put in lambda sub 1, and we know this is 0 when you put in lambda sub 1, so this is 0 when you plug in our solution, as well as the evaluation here at n plus 1 and n plus 2. When you plug all that into here, you do in fact get 0. So this is a check that our, what we called a guess at the beginning, actually proves out, and we actually do get a solution. Okay, so let's move on to finding a specific solution when we have two initial conditions. We have two initial conditions, and that'll allow us to find values for c and d from our general equation down here. So the conditions are x sub 0 equals 1 and x sub 1 equals 1. And that leads us to this Fibonacci sequence here. The third term is the sum of the first two. The fourth term is the sum of the second and third, and so on. You just sum the last two and get the next one. And that's what our formula initially said, if you think about it for a second. So I gave names to the lambda sub 1 and lambda sub 2, phi and psi. Not my choice, but that's the general terms that are used in the literature for these ratios here. We have a few identities. If you add these together, you notice the square root of 5 over 2 cancel, and you just get 1. If you subtract them, the minus 1, the 1/2 cancel, and you just get the square root of 5. If you take 1 minus this, you get psi. And then this one here, you need to do a little bit of work. If you take the negative of this and the reciprocal, then you need to multiply it by 1 minus the square root of 5 on the top and the bottom, and then do some algebra, and you'll see that these two are equal here. Okay, so we have our solution, our general solution, and then we're told these two initial values. We put in 0, x sub 0 is 1, then we put in 0 for n, and you just get c plus d equals 1. Then you put in 1 for n, you get x sub 1 is 1, and then you get 1 here and 1 here. And again, I renamed these, so it's just c times phi plus d times psi. So you have these two equations, and it's a matter of doing a little bit of algebra to solve these two. I left out the details, but when you do that, you get C equals phi over the square root of 5, and D equals minus psi over the square root of 5. The last step is to plug our solutions, our values for C and D back into this here. So we put in C, D here, then lambda 1 was phi, and lambda 2 was psi. Just to remind you here, the Greek letters, the pronunciation, I forget myself, so I wrote it down here. And then you get x sub n equals this here. And then we can actually plug what phi and psi are into here. And that's our general solution. So the first time I saw this, and even now, it's kind of amazing because we know xn is 1, 1, 2, 3, 5, 8. It's all whole numbers. And yet the expression for the x sub n is this thing that has irrational numbers in it and powers. You know, it seems highly unlikely, but if you even take the case like n equals 2 or 3 and multiply it out, you see that things cancel and you actually do get whole numbers. Here's just check for yourself. Of course, you won't want to multiply this out to the 13th or 14th power, but if you use the calculator, you'll get exactly 377, or you know, very close if there's some rounding off. But if you actually did the expansion and the cancellations, you would get exactly this. This is not an approximation. This will exactly give you the value x sub n if you go through all the algebra. And of course, it gets harder and harder as n gets larger, and you're bound to get approximations if you're just using a computer or a calculator to compute these. Okay, so kind of an interesting example. We can change the initial conditions and use the same difference equation, and we'll get something called the Lucas sequence. We'll solve that one also, and let's have a look at that. So we'll start with the same recurrence difference equation here, which I copied down here at the bottom. And the only thing, and we'll have the same general solution, which I've also copied down here, with the particular phi and psi is the solution, lambda sub 1 and lambda sub 2. The only thing I've changed are the initial conditions. So now x sub 0 is 2, and when you plug that in here, you get 2 equals c plus d. And then 1 is the same as before, so you get this here. And when you solve this, you get c equals d equals 1. And so this becomes x sub n equals phi to the n plus psi to the n. And that generates this sequence here, which is known as the Lucas sequence, Lucas numbers sometimes. So it's just starting differently, and then, of course, the numbers that follow are different also from the Fibonacci. In this example, we have a repeated root. We have this difference equation, and if we let x sub n equal lambda to the n, and then divide out the lambda to the n after we plugged it in all three of these here, we get this equation, which factors as lambda minus 3 squared, so we only have one root, and that can't give us two independent pieces. One piece is 3 to the n. We need another independent piece, and that we get that by multiplying n times 3 to the n. So this is our general solution, 3 to the n times d to the n plus c. And we can stop here, but if we want a particular solution, we need two initial values, and that's what I've supplied down here. If we let x sub 0 equal minus 2 and x sub 1 equals minus 3, then we can compute a specific solution. You notice when you put in x sub 0, the d cancels out altogether, and you just get 3 to the 0, which is 1 times c equals minus 2. So c equals minus 2. And then you come back a second time and you put in 1 for n. X sub 1 is minus 3, and I left out the algebra, but it turns out that's d equals 1. So you plug that back into here, and you get this solution, or you can write it like this here. Okay, so that's the general solution for this particular equation. And in general, when you have a repeated root for a second order, you take the one root to the n power, like we did here, 3 to the n, and that gives you one component. Then the other component is n times 3 to the n. I'm not going to prove that that works, but that's the general technique here. All right, so we have one last case. That's where you have your characteristic equation has complex roots. And there's a way of handling that also, which I'll show you. So the third case is where we have complex roots, and they would be of this form here, alpha plus or minus I times beta. I is the square root of minus 1, complex imaginary number. And so we just plug that in as we would for real roots. So it's c plus alpha plus I beta to the n, and d times alpha minus I beta to the n. Then we do a little bit of transformation to get this in a better form, or an easier form to work with. So we convert the roots to polar coordinates. So we let alpha equal r times the cosine of theta, beta equal r times the sine of theta, where r is alpha squared plus the square root of alpha squared plus beta squared, and theta is the inverse tangent of beta over alpha. So this is the standard conversion of a real number into or a complex number into polar coordinates. Okay, then we plug that back into here, and so we're going to get things like r cosine theta plus or minus I r times sine theta. The plus is for the first one here, and then the minus is for this one. And then we have an identity from Euler's formula. So what's inside of here is e to the I theta or e to the minus I theta. And the nice part about this is when you raise it to the n power, you don't need to deal with this. You can just identify this as r to the n e to the plus or minus I n theta, and then convert back using this formula again to get r to the n cosine n theta plus or minus I sine theta. And then when you plug this, the plus one into here and the minus one over here, and then you collect the cosine terms. So this here, c plus d cosine, and then you collect the sine terms together, and then this is your general formula for the difference equation that has of order 2 that has complex roots. This is the general format. So you need to know the initial values in order to get this exact for C and D. And I have an example of this on the next slide where we actually compute all the parameters. On this slide, we have an example of a characteristic equation with a pair of complex roots. I copied our general equation up here. This is our particular problem. And when we plug in lambda to the n for x sub n, and then divide out lambda to the n, out of all three terms, we get lambda squared minus 2 lambda plus 2 equals 0. We plug that into the quadratic equation, and we get 1 plus or minus I. This is fairly easy to translate to polar coordinates. The modulus is the square root of 2, and if you graph this, it's just 1, 1 in the complex plane. So the angle is pi over 4, or in the minus case, it's minus pi over 4, but we take the positive one for theta. Then we use our initial conditions here. We put in n equals 0. We get r to the 0, which is 1. Sine of 0 is 0. The cosine of 0 is 1. So you just get c plus d equals x sub 0, which is 2. then you plug the this into the equation again. So when you put in 1 for n, you just get r, which is the square root of 2. I have that out here. And then 1, it's 1 times theta, so it's the cosine of pi over 4 and the sine of pi over 4 are both the square root of 2 over 2, so I factored that out. And then you just get c plus d plus I times c minus d. And we know that c plus d is 2 from this first equation, so we have this here equals 5. And you can just subtract the 2 from the 5 and you get I times c minus d equals 3. And we don't even need to solve for c and d because what we need is c plus d, and we have that. That's 2. We have r, that was the square root of 2. Raise that to the n power, and then I times c minus d is 3. So we just plug that in here directly, and that's our equation. On the next slide, I show you a graph of this. Yeah, so here's our solution, and then I had it graphed. This white line here. It's a little bit hard to see before you hit 8. So this is a blow up, and it's sort of an exaggeration of here, but it's already like 1 oscillation when you hit 8. And then you're going up again and down again. And it's basically bounded by plus or minus the square root of 13 times the square root of 2 to the n. So it's this dashed line here and here. So this is just getting wider and wider, and the oscillations are getting bigger and bigger. And that's generally the type of solution you're going to get when you have complex roots to your characteristic equation. So quick summary of this lesson. We use this technique of guessing the solution was lambda to the n, and then working through the algebra, solving, in our case, the quadratic equation. We have 3 cases: distinct roots, repeated roots, and complex roots. In the case of the distinct roots, we looked at the Fibonacci sequence, the Binet formula, which was rather surprising because you have these irrational numbers that in your formula that actually give you whole numbers when you multiply them out. We did a variation of the Fibonacci sequence known as the Lucas numbers. And then we concluded just now with the case where we had complex roots. So in lesson 5, we'll add back in the forcing term, the b of n, so it won't be 0. In that case, the solution splits into a complementary and particular part. So first we solve where b of n is 0, and then we have to account for this b of n. That's what this is referring to here. The method of undetermined coefficients and a table of trial solutions. The trap that makes the method fail on a first attempt. So we'll talk a little bit about some possible ways you can go wrong. And then 2 full-worked examples, one of which reappears in the Gambler's Ruin problem. So I have you may not know what this is if you only looked at this series of playlists. I have another playlist on stochastic processes, and a couple of lessons are on what's called Gambler's Ruin, and it's a probabilistic problem, but when you write down the problem, it's actually a difference equation. And so from that series, I'm pointing back to to this series here, and I guess from this series, if you're looking for more extensive examples, I would point you to my playlist on stochastic processes. And I just have a note here that the lesson 5 opens with the difference equation of this form here. So this has got like all the bad things in it. It's k, order k, right? You're starting with n and you're going up to n plus k. So it's order k. It's non-homogeneous because the B of n is here. And then the way we've written these coefficients, they're functions, so it's also not autonomous. So we'll look at that in lesson 5. And then there's one more lesson after that, lesson 6, that'll conclude this playlist.